background you have will help facilitate your understanding. Okay, so just have your stuff on your desk, have your kinetics all screwed up flat on your desk. And then this is the last slide that we did not, or this was close to the last slide we didn't get to yesterday. It is on the very bottom of that first quadrant. You with me? All right, so yesterday we talked about graphs. For all the axes that we've seen so far, what were the axes of those graphs? Like, what was the y-axis? Maybe not from the lab. Concentration, which was number of screws, right? So it's a concentration. So it's a quantity. And what was the x-axis? Time. So it is this a rate by taking amount over time. So change of the amount being clarity most time for us over time. So sometimes we don't have to find, sometimes we're given graphical data, we can find the rate of reaction. Other times we'll be given information, we do a comparative rate. So if we're finding absolute rates of reaction, we always can quantify that per reactant and per product. You just have to change the way you write it. So if I said the rate according to A is negative, why is it negative here? Because it's a reactant, so we adjust the rate by putting a negative in the front because it'll make it an overall positive rate, because we always express rates as positives. And then we do 1 over A. What's this little A representing? The coefficient here, right? Is equivalent, 1 over the coefficient is multiplied by the change in the reactant A over time. This setup, if we do it for B, C, and D, will create one rate quantified based on the reactants we have. So it relates to the stoichiometric relationships or the mole ratios that we have. So if I said this was true for A, what would be true for B? Write the rate for B. Negative 1 over lowercase b times the concentration or change in concentration of B over change in time. So you're just modeling the same way. So we're just writing the rate with respect to each reactant, each product. Keep going. This is equivalent to, so a positive 1 over C delta concentration of C over delta T, and then so forth. You can write the last one, 1 over lowercase d, change in concentration of product D over change in time. So, given real numbers and real concentrations, we could utilize this relationship by looking at the coefficients to see, like, we produce something at either the same rate as a product, or we produce it as half the rate, or 3 times as fast. So we can use these numbers as quantitative and qualitative comparisons. So that's just going to really make sure that when we're talking about the rate of reaction, we can adjust it based on the identity of the reactant product to relate all to one rate number, and that same rate can be used for any A, B, C, or D as we quantify it based on the numbers that we have of them. Okay, so we're going to talk about this in a second. Actually, right now. I don't think that examples in yours. No. Okay, write down this reaction first, so you have the example in front of you. And then just verbally tell me, like, a couple of words. How does the rate of formation of nitrogen dioxide compare to the rate of disappearance of dinitrogen tetroxide? The rate of, what do you want to say, appearance or disappearance? Appearance is 2 times as fast as the disappearance of dinitrogen tetroxide. Appearance of, there we go. All right, so that's just a verbal explanation of what the coefficients represent. Thumbs up when you're okay with that. It makes sense because we know what mole ratios are supposed to represent. So we're looking at the 1 to 2 ratio and identifying the rate of disappearance or appearance and disappearance. Okay, so for this one down here, write the rate law, which is like what I just wrote. Rate is equal to negative 1 over blah blah blah. Write it for this one, the oxygen and ozone one down here. So we're saying rate is equal to what? Start me off. Negative 1 over 3 times the change in the concentration of O2 over change in time. Okay, so that's just with respect to the reactant of oxygen. And then we've already incorporated the 3 as we put them on the same playing field, so we divide by 3. This is just like limiting reagent when we divide by its coefficient. Keep going. Equivalent to positive 1 over times delta concentration of ozone, okay, over delta T. Okay, yeah. So as we, this is the disappearance. So we write a negative here to show that the disappearance of this oxygen, when we change the concentration over time, it's going to be negative, like oxygen final minus oxygen initial. So we multiply those two negatives to make a positive, because rate's always expressed as a positive number. So when we add it, when we're producing or making things appear, it's already positive. So we don't put the negative in front, because then it would overall be negative, which would be incorrect for the rate. So we just put the negative and the positive separately. Negative for reactants, positives for products. Okay? All right, so those are 2 ways so far. Verbally, or like, sentence form, and then like this. And then I have one more for you, but we're going to solve like numerically for the rate. Okay? So at a given temperature, the rate of appearance of ammonia is 2.0 times 10 to the negative 3rd molar per second. What is the rate of consumption of nitrogen and hydrogen separately? So go ahead and write the balanced chemical equation first for me. So I give you the 2 reactants, and I give you the product. All right, William, give me the reaction.
2 plus 3 equals 2.
Good. Okay, so there's no fractional coefficients in kinetics generally. It's just going to be like what we normally would do in honors chem. But we now have ratios that we can utilize to compare the rates. So the rate of formation or appearance is 2.0 times 10 to the negative 3rd molar per second. And this is with regard to ammonia. You guys can tell me what's the relationship between ammonia and nitrogen. 1 to what? 1 to 2, right? Okay, so if you're forming at this rate, what do you think the rate of disappearance would be for nitrogen? More or less than this? Less, because for every 2 of these formed, you're only using up 1 of these, right? So how less? 1/2, right? So all you're really doing is multiplying by the mole ratio. You're just going to say 1 nitrogen is utilized for every 2 ammonias formed. And I'm not doing mole ratios necessarily because this is molarity and this is seconds. We're just multiplying by the ratio to include now ammonia is gone, to now include the rate as it with respect to nitrogen gas. So it should be half, right? So 1.0 times 10 to the negative 3rd molar per second. This is the disappearance of nitrogen. So all we did was modify with what we talked about the rate with respect to. So how would you do nitrogen or hydrogen? What am I writing? Okay, so 2.0 times 10 to the negative 3rd molar per second times 3 over 2, right? So 3 hydrogens are utilized for every 2 ammonias. You got this. No calculator, come on. 3.0 times 10 to the negative 3rd molar per second. And this is the disappearance of hydrogen gas. Cool? Alright, so those are things people forget at the end of the day, like when we get done with kinetics. You'll sometimes forget that you can relate things through mole ratios, because we won't do that pretty much anymore. But just maybe put a star on this, like, look at before the test, because this is something we teach early, but we don't really review afterwards. Okay? Alright, so kinetics, all screwed up lab. Okay? So let's talk first about R squared values. Okay? R squared values. See if my computer's going to work here. Alright, so the bold questions at the top, you could have probably, you should have been able to attempt, especially like writing your own steps out, okay? So in round one, give me some R-squared values, guys. Kind of just going, I'm going to go down the rows. Give me some of them. Over here, R-squared values. This whole area, like whole area right here. 0.985. Keep going.
0.986.
Ooh, okay. Keep going. Down here. Where'd you go? Same. Okay, give me some different ones. 0.997. 996. Okay, one more. One more. 0.978. Okay. Okay, so very clear. It's very clear now. We track, or we put an L1 and L2 quantity of screws and elapsed total time, right? Okay, so that can be related back to like concentration versus time. So what does R squared tell you mathematically about the relationship between these two variables? Correlation, right? But we graphed it a very specific way. How do we graph it? But we're looking for linearity, right? So you guys did y is equal to mx plus b. So we did a linear regression to see how best fit this relationship was. Was it really good? Yeah, it was pretty dang good, right? So this is a very linear relationship. And so the value of having linear relationships is that we can do a lot of prediction and we understand linear relationships a little bit better than like logarithmic and natural logarithmic and exponential relationships. We have a lot of predicting power here. Okay? Yeah.
Why would it even be because if you said that when there's less of concentration.
Hold on. We're gonna get in a second. So that's what I want you to tell me is if this was the relationship, it showed that the number of, I'll put the number of concentration of nuts, right? Because it was those that were changing over time. The number of screws were really what you were putting on. So what do you guys conclude then if that was a linear line? It kind of looked like this. What would you conclude the relation, or let me phrase this. Did the concentration of nuts affect the rate of reaction? Yes or no? I see a lot of people saying no, right? So it was linear because no matter the number of remaining nuts that you had left, overall the slope was fairly constant, right? So it didn't matter if you had 10, that was the slope, right? What does slope mean to us in terms of this relationship? Changing concentration over time, which means rate of reaction. So this means rate, because rate is change in concentration over change in time. Okay. So the rate was, I don't know what your rate was, but if the rate was this at the very beginning when you had a lot of quantity of reactants, and it was the same here and the same here, did the concentration of nuts impact the rate of reaction? No, it had no influence on it. So we would say that rate is independent. You might want to write down some of this as we go. Rate is independent of concentration of, in this case, the nuts. So we could say that about any reactant. So if the rate is independent of the concentration of a particular reactant, we say that with respect to that reactant, it is zero order. Okay, so that's what we say. When we say zero order, the concentration of that is zero order. We mean that it doesn't matter if I have 1,000,000 of them or 1,000,000,000,000 of them or one of them. The rate will always be the same no matter how many reactants I have. Does that make sense so far? Kinetics, the order thing sometimes is hard to grasp. Okay, so we saw that the linear relationship existed, so we made this assumption. So then we had to rationalize what does that mean. So we looked at our slope, what was, give me somebody's slope. Give me your M value. Anybody write it down? It might still be in your calculator.
Negative
19.82. So I'm going to show the slope as negative. I'm not going to write as negative for the moment because remember, rate we don't express as negative. So what we are showing here is that you could have done. Did you guys graph it per second? Per second? You guys do per minute. Well, no, like it would be concentration over time, right? So it would be number of screws per second. So you guys did 19 per second? Is that what that means?
This was for round 2.
Okay, give me round 1. Sorry, we're working round 1 for a minute. Anybody? Yeah.
Negative 0.0679.
That makes a lot more sense. 0.0.
679.
Okay. So this is like, you guys didn't even screw 1 per second. That makes a lot more sense, right? Because you guys were like fiddling with it and trying to orient it the right way. So I have it looking like a little bit of a steep slope, but that's really the slope. So in terms of what this means in terms of the kinetics or the rate law, I told you guys yesterday rate law was just we wrote rate, and we set it equal to something. Well, we've written it a couple of different ways today, but here's what this looks like. Rate is equal to little k. Remember I told you little k yesterday was not big K? You're going to say little k times the concentration of the nuts to the 0 power. That means to the 0 order. So that's what the rate law is for number 1. And everybody's data suggested that because we said that rate was independent of the concentration of the reactant. Okay, but how can I simplify this? Rate is equal to just k, because the concentration to any 0 power is just going to be 1. So then rate is equal to k. So what you have here is rate, right? And you guys just said this, the slope was this. So technically, isn't this concentration change over time? Right? So that rate should be molarity over seconds or concentration change over time. So that is your rate. That's how slow you guys were for round 1. And it makes sense. You weren't able to achieve it very quickly. Okay, so you got those pieces together for round 1, right? Okay. A question that was asked of you to consider was, in terms of the many, many steps you took, and you guys wrote down your detailed procedure, like how you put it together, we call that your mechanism. So what was the first step of your mechanism? Okay, so say again. Grab a screw, okay, and grab a nut, and then, okay, so connect in the correct rotation, right? And then spin with intention to, make a good contact. And then use what? What did you say? What did you say? Yell at the person to speak faster. Okay, so you were trying to get this thing on. Well, it took a certain amount of energy to pull them together, right? But just because they collided, did it mean that they reacted? Okay, so we reacted. So we collided the correct orientation, and then how did you achieve the transition state? Well, no, but we weren't to the transition. That was like we met the transition state, but you had to apply a certain amount of energy, like screwing it on, right? So what does that supposedly represent? Activation energy, right? It took to get all the way up to transition state, and then you said, done, throw that thing down, we made a product, right? So that was the goal, to see that there were many steps to our reaction mechanism. Which step was the slowest step for you guys? So probably the orientation piece, right? Some people were super fast because they were like flinging it and trying to, screw it on pretty fast. All right, so in the reading that you guys did, there was a phrase for the step that slowed us down. Say again? The rate determining step. Yeah, so the term used to represent the slowest step is the step that slows us down the most determines how fast we go. We call that the rate determining step, or RDS. Did anybody pick up on that terminology from reading? A couple of us are like, okay, yes. So if, okay, so, all right, Drew, we're going to call some people out, okay? So I am, right? So, no. Is it I am when 4 people do it?
4.
Not individually. So the team,
relay.
yeah, so medley relay, right? Okay, does anybody else swim in here?
William did.
Okay, well now, okay, so we can call people out, okay. So who's the rate determining step on your team medley? Yeah, it's fine. I mean, I would say probably be the butterfly. It's probably one of the harder ones to do. Right?
The determining step would be breast. Breast is slowest.
Okay, so whoever's doing the breaststroke is probably the rate determining step, because they basically, overall, it's no matter how fast the individual steps are, the slowest step determines the rate, right?
Yeah.
The slowest step basically says like this is the rate we have to go.
Yeah, but if every other relay is doing the same thing.
but if every other relay is faster, the one that determines how fast your overall is.
So wouldn't the rate determining step be the one who's slowest compared to all the other people swimming?
But we're looking at just your mechanism. We're not looking at all the other teams.
Okay.
Just yours. Okay. So I would be the let's be honest. I'll be the rate determining step on a cross country team or a track. You know, passing the baton. That orientation's probably not going to hit. I throw the baton at somebody. Okay. So we're going to talk about the other one too. I'm going to race into this. Okay. So you guys got what you need for round one. All right. So I hope that you're writing down some of the details with me. What were your for round two? What were your R squared values? 0.97. Okay, keep going.
0.93.
Okay. 9.4. Keep going.
9.5.
9.5. Nobody got worse than 0.9. Okay. 9.2. Okay. All right. Well, theoretically, these are not as linear, right? The relationship between concentration versus time is not as linear. So what we can do, and this is what the question said, how can you manipulate the mathematical relationship to show more linearity? How could you manipulate it? So what we could do is, do you guys still have this data in your calculator?
Yeah.
Yeah. What we could do is we could now express this, and I'm just going to tell you, express this as the natural log of the concentration. So I think if you go to L1, you can do, or L1, you can just put L1 at the top, and it should apply it to all your data points. Is that right? My calculator's fancy. I don't know about y'all's. Okay, so theoretically, this is actually the most linear relationship. Sorry, I didn't apparently sleep last night. I can't do this. Okay. So in the way that we've drawn it here, it would not be concentration versus time. It wouldn't be this linear. It would be actually more linear if we applied it to the natural log of the concentration versus time. So what does it kind of look like if we graph it like this? What does this look like? Say again? A reverse what?
Oh, I said like an upside down cubic inch. So it doesn't matter.
Well, okay, let's dumb this thing down. Right? Does this look like a straight line or a curved line?
It's a curved line.
Slightly curved. It should be slightly curved, right? When you do concentration versus time, because as you because let's think back. Let's say that the very beginning you had 10 appropriate nuts and then 10 of the two small ones, right? Okay, so you pretty much had a 50-50 chance of grabbing the right one, and you put it on, okay? But as we went along, I think Miriam can attest to this. As we went along, what was the problem?
There was more odd ones, or like ones that didn't work. The ones that did work.
All right, so there were more incorrect ones than correct ones. So as we went along, we decreased our concentration of the correctly fitting net. What happened to our rate? Did it increase or decrease?
Decrease.
Right, we got a lot slower because we couldn't grab the right one, and so we went longer and longer and longer and longer between successful collisions. So it was fast, and then it was like, oh gosh, oh crap, we can't find the right one. Miriam, come on, hurry up, right? So we couldn't slow it. We were slowing down as we were going. So did the rate depend on the concentration of the correct net? Yes. Okay. So the rate is dependent on the concentration of the net now. So then we must change how we write our rate relationships. So we're going to change that, and it's not going to be zero order. I'll tell you that since we graphed it as as a natural log, it's going to be first order. Later on, we'll distinguish between first and second. But now I write the rate law as rate is equal to K, concentration of the nut, to the first power. So the first power is representing my relationship in first order. Okay? All right, so I'm going to stop on this for a moment. I'll take more questions on this at the end of class. I would like to talk about differential rate laws, which they're actually pretty easy. We practice a couple together, so then you guys can practice on your problems. You with me? So that was the next set of notes. But being able to explain rate dependency is something that we'll need to be clear on, so that's why I'm going to talk about that first. Okay, so we call these things differential rate laws, but in the end, we just call them rate laws. Like, we know there's a difference between differential rate laws and integrated rate laws, which is yesterday I was speaking a little bit about the calculus behind it. In college, you have to maybe run through the calculus because they're so prereqs for college courses. But I'm just going to show you the relationships and help you understand the mathematical background. But if you are in calculus, you might think a little harder and say, oh yeah, I know what this means mathematically. Okay, so when we're talking about rate laws, we are talking about the relationship of concentration of the reactants. We have to be very clear. We're not talking about the products at this point anymore. We're talking about how reactants control the rate, because the reactants are going to have to collide to force a production of a product. So some reactants are more important than others in kind of controlling how fast something occurs. So we do have to identify the orders or the impact that each individual reactant has on the overall rate of formation of products. So that's why I have reactants really big, because I really want you to be sure you're only talking about reactants here. Because when we get to equilibrium, we're like, products, what? We talk about products now, so it's going to be a different story. So every single time we do rate determination, it all has to be pulled from experimental data. We can't just look at a reaction and go, yeah, okay, well, the 2 there's and 3 there, so it must be second and third order. We cannot look at a reaction and look at coefficients. Everything is experimentally driven. So when I do get the experimental data, I'm just going to have a data chart, and that's what I look at to determine the orders of reaction. So what I'm talking about when I say orders, I'm talking about these coefficients, or these exponents up here. Like, for example, x and y. We put real data in there and find them, but x and y is what we're looking at. So for this reaction A plus B yields C, I have reactant A and reactant B in there. I'll identify their orders of reaction experimentally, and I'll plug that into the rate law. So I'll say rate is equal to little k, which, what is little k called? It's on the board. Rate law constant. Okay, so little k is called rate law constant, and I'll take that data. I can solve for k, I can solve for rate, I can solve for basically anything in here given the data. The only other thing, and I'll tell you more, but there are other things that can impact little k, rate law constant. The most important thing is that it is temperature dependent. So we will always establish this. We'll say like, oh, here's the rate law at 298 Kelvin, and you'll say, oh, do I need to do something with the Kelvin? No, you don't. It's just a really conventional way of always getting all the information, the big picture. They'll always say a temperature, but it's not really relevant to our problem. We'll just understand that if I went from 298 Kelvin to like 400 Kelvin, what do you guys think would happen to the rate? Why do you think it'd speed up? Because high temperatures cause, well, higher kinetic energy, which cause 2 things. Increased frequency of collision and, right, the greater force of collision, which would meet activation energy. Remember, temperature has 2 factors, okay? So yeah, duh, if you increase the temperature, the rate's going to increase. So if the rate increases, it's probably going to be, the K is something here, the K is going to be larger here, and that would then, since the K is correlating with the rate, it would cause the rate numerical value to also be higher. So there is a temperature dependency here. Okay. Remember that coefficients do not matter for us right now. The coefficients are what we'll use with mechanisms in a couple of days. So differential rate laws, we always compare concentration versus rate, which, remember, rate includes time. So you'll have a table with data in it, and this is the data we would have, concentration and rate data. You might have time as well, but it's not, no, you wouldn't have time. You just wouldn't have time, because time's going to be integrated rate law. So like Monday, Tuesday, we'll learn about integrated rate laws, and this is very clear it's integrated because we're integrating with reference to time. So they'll have concentration versus time on their tables. So when I show you the data table, you first look and say, okay, it's concentration and rate. This is a difference in rate law table. If it's concentration versus time, this is an integrated rate law table. But they all relate to each other based on the orders that we speak of. We just need to understand that they're representing the same thing, but through different data. I told you guys this yesterday. We are always speaking to the initial rate of reaction, because what happens over time? It probably slows down because what happens to our reactants over time? They decrease, and then, if you're looking at time 10 and I'm looking at time 20, then we'll be talking about different things, and it would be difficult to communicate about that reaction. We will eventually talk about the mechanisms, but the mechanism pieces will come shortly. All right, so is this example in your paper? Yes. All right, so looking at the rate law, looking at this rate law right here, you'll notice there's some exponents. What are each of the exponents here? This one, 1 hydrogen, 1 and bisulfite, 2, right? Okay, so just make sure you guys can see those. Those are the orders, okay? So what's the order with respect to H0? 1, good, so you're looking at the exponent. What's the next order? 1, and then the bisulfite, 2. And then what do you guys think I would consider doing if I'm looking for the overall order? Add them up, that's it. Okay, so what's the overall order? 4. We don't see fourth order very often, but we will just add up orders. Okay, so given this rate law, go ahead and look at the reaction that this correlates with. Sorry. So looking at the reaction it correlates with, you'll notice there's a lot of other coefficients involved. This is probably like a redox reaction. You can probably see some of the similarities we saw before with chromium, 3+, we see the H's, we see some oxidation state changes, but you could be given a redox reaction and then also given data for a rate determination, and you guys could find the rate of that reaction. Notice the coefficients do not correlate with these, which is why the big point here, we have to have experimental data to determine what we're talking about. All right, so here's what I want to talk about first. If the rate's equal to these independent concentrations to some order or to some power, you have to think about what's going to happen to the rate if something changes within the concentrations. So if hydrogen ion concentration doubled, okay, so if I take H2 and I double it, doubling it to the first power is still what? 2, right? So 2 to the first power is still 2, okay, so then what happens to the rate? So you're taking 2 to the first power, which is 2, so that's going to impact the rate by multiplying the rate by 2. So what happens to the rate? It just doubles, right? Okay, so that's easy to see because of the relationships between concentration and rate. All right, talk about the next one with the person next to you. And maybe that first one if you didn't quite get it. Give me a thumbs up when you're good. Okay, most of us say yeah, but let's see. So if I take the concentration of bisulfite and I multiply it by 2, it's not just going to be 2 anymore. What have I done? I've squared it, right? So I'm multiplying the concentration here. Concentration, I'm timesing that by 2, but all of that is to the second power because of the order. So that effectively means I'm doing what to the overall rate? Quadrupling it because 2 to the second power is 4, so I'm going to quadruple the rate because the rate's equivalent to these concentrations to some power. Okay, keep going. Actually, now I'll tell you this. If I had, let's pretend there was some extra thing, like potassium ion, and it was to the third power, to the third order. What if I doubled the concentration of potassium? How would that impact the rate? I hear 2 people saying 8, right? So if I take this and I multiply it by 2, that effectively means I'm taking potassium ion times it by 2, but to the third power, so that's 2 to the third power, which is 8. So I would then adjust the rate 8-fold. You with me? 8-fold means times, I don't know what the word for octuplet, like quadruple, octuple? Octuple. You guys like that one? Okay, we'll keep that. So I would just say 8-fold because I don't know the word for 8 times that, okay? Okay, so there's a little bit more here. So if we have a little k value in each of these rate laws, the little k values units actually help us determine the overall rate units. Well, what's the rate unit? Always molarity over time, right? Okay. So if rate is molarity over time or molarity over seconds, a lot of times we use seconds. It can be used minutes and hours. And what does bracket mean again? here because I can write not on top of stuff. So bracket means concentration. So based on multiplying by molarity, what does the K units have to be in a first order reaction? Well, I already got molarity, man. Look, I got molarity here. That's still the same molarity. It's just there. I'm setting units equivalent. So what does K have to be? Say again? Say again? Per second. Sorry, you guys gotta be louder. I'm deaf. Okay? So 1 over seconds. So K has to be 1 over seconds in a first order rate law because it's the only way you're gonna end up with molarity per second, which ends up being what our rate information is regarding. Okay, so figure out the figure out the units for the K's in 0 order and with this one, this will be third order overall. Figure out what the K units would be. Work with the person next to you. We can do it. All right, come back to me. 3, 2, 1. All right, everybody should have the 0 order one. What is, if this is to the 0 power, what is A? Just 1, right? So the molarity to the 0 power, we're going to call that 1. So that's out. That's gone. So that's why I've written it like this to show you the simplified version. So if rate is molarity per second always, what is K here? Molarity per second, right? Okay, so in a 0 order reaction, K is molarity per second, or molarity per time. So for this one, rate is molarity per second. K, what are these collectively? Molarity to what power? Well, okay, so I'll do it separately. Molarity squared times molarity to the first. Well, simplify that for me. So K times molarity cubed. Okay, so I've got K times molarity cubed is equivalent to molarity per second. Okay, say again. Seconds can't be cubed because seconds can't change. It's just per second. Over seconds molarity squared. Good. All you're doing is isolating K, right? Divide by molarity cubed, right? When you divide by molarity cubed here, you're also dividing by molarity cubed here, which is going to be, in the denominator. So then simplify that. 1 over molarity squared seconds, right? So that's equal to K. You do have to work out the units of K each new problem because they don't always stay consistent because it does vary based on the order of reaction. Thumbs up if you understand unit matching. Like you're taking the units of 1, you're setting equivalent to the units of a number of things, but you just have to simplify them down. All right, we will work on those with real problems because it looks like I got half class here. Okay, actually, turn and talk for a minute and talk about this one. See if you can explain to the person next to you. I just want to make sure we're on the same page.
Why does she like that? Or whatever the it says 0 but if that's the when yourself already was so then the way she has it molarity
Okay, come back to me. Shh. All right, so we just did the piece down here. So we already understand how to manipulate the units, but you might want to write down a little bit more about what the K constant is going to be manipulated by. So we know it's a constant, right? It's a constant for a specific temperature. So when you vary the temperature, stuff gets faster, the rate gets faster, meaning the little k gets larger. And there are a couple of other things that it depends on. It depends on how strongly ions or other things can be bonded together. So if it takes a while to kind of overcome that bond, it will slow the rate down. So that will be reflected in our K as well. Those are the other two that are well, generally there's more than that, but those are the other two that we generally regard that will manipulate K. And then we just said this, it will fit the math of the reaction system, so that rate will always equal molarity per second. All right, thumbs up when you're good here. Yeah. It's a constant at a specific temperature. So we'll utilize that same constant through the entire problem at a given temperature. We just like to say it's a constant because it's a constant while the other variables of the system are changing. So the other variables of this system are concentration and rate. If we keep this constant and we can change the concentration, we can call this the independent variable, right? The independent variable is what's controlling the dependent variable over here. So remember, like in true experimentation, you always have one variable you change. It would then be reflected in the dependent variable while everything else is staying constant. It's constant at a specific temperature for a specific reaction, but we always we call it a constant so that we can manipulate two of the variables, and that's it for experimentation purposes. Because everything rate law related is all determined experimentally. Okay. Okay. Here's the table, right? So I told you, what would you see in the table? Data for what and what? Concentration and rate, right? So you see concentrations and rate. These are just trials to say, like, I've done a number of trials for this particular reaction. So I have a reaction A plus B making products. The rate is molarity per second. So I've got time embedded, but it's not independent. What you do is something called table logic. First, watch how I run through table logic so it makes sense to you, and then we'll do some more examples. So, I've already given myself some hints on what I'm looking for. Basically, in an experiment, you keep one variable constant, you keep all variables constant except for one that you'd like to change. So the one I'm changing from trial 1 to 2 is the concentration of A goes from 0.1 to 0.2 molar, but I'm keeping B constant. Okay, so how am I manipulating A? I'm doubling it, so I'm multiplying the concentration by 2. How does that impact the rate? Oh, it multiplied it by 2 as well. So what does this, so this is the concentration of A multiplied by 2. What power does that have to be? 1, right? So you already know the order of A. What's the order of A? First order, right? So because this was constant, I can say, like, this doubling caused this doubling, so this must be to the first power to cause the rate to double. So I like to go ahead and do this, to just indicate now I know the order of the A reactant. So I want to keep something else constant and change something else to see how that impacts the rate. So if I kept B constant first, I'm going to keep A constant now. So which two trials do you guys want to look at? Let's do 3 and 4. Okay, so between 0.3 and 0.3, just for myself, I draw them as straight lines to show they're constant. So, but then from 3 to 4, trial 3 to 4, what's happening to B? It's doubling, okay? How does it impact the rate? All right, quadruples. Okay, so what power could this had to have been? To the second power. So to the second power caused the rate to quadruple. So what order is B? Second order. So this is called table logic. You're looking at the table, you look for constants, you look for one variable to change, and you see how it impacts the rate. Okay, so what's the rate law? Rate is equal to, I'll write it over here for you. Rate is equal to K times A to the first power times B to the second power. So we experimentally found rate is equal to little k, A to the first, B to the second. With me? Okay. So additionally, from determining the rate law, we also want to find the value of K with its units. So what you would do, and I indicated this someplace, maybe I didn't, yeah, use data from one trial and substitute it into the rate law, and then find little k value. So I always plug in the first trial, so if you're ever looking at my work, it's usually the first trial. So what's the rate for the first trial? 0.2 what? Molar per second, right? Okay, equals K, because I don't know what K is. What's the concentration of A from the first trial? Point what? 0.1 molar to the first power. What's the B concentration for first trial? 0.1 molar to the second power. Okay, so I have all of my variables plugged in, I solve for K. Correct? Okay, so what is this? I'm going to pull this together in scientific notation. I'm just doing this in my head for now. What's this? Point one. Well, so what's so point one cubed, right? Okay, so what's point one cubed? Okay, 0.001. So is that 1 times 10 to the negative? Whew, gosh. Okay. What's happened to molarity? Molarity is what? Okay. So that's 1 times 10 to the negative third molarity cubed. So I'm dividing by that now to isolate k, right? And I'm using exponents because I want you to see how you can do this if you can do it in a calculator, but you don't always have to, and you can't always. Okay, so I have 0.2, which is technically 2 times 10 to the negative 1. Okay, so what's 2 divided by 1? What's 2 divided by 1? Woo, 2. Okay, so I'm gonna write that up here. That's 2. 10 to the negative 1 divided by 10 to the negative third. What do you do to exponents? Subtract. Negative 1 minus the negative third. Positive 2. Okay, so times 10 to the positive 2. Okay, what's molarity divided by molarity cubed? On the top or bottom? Bottom. And then what happens to the seconds? It just stays, right? This is actually over 1, so that's why this stays together. Okay, so that's 200 per molarity squared seconds. Correct? Huh? There's no unit. K is a weird system, right? K, you have to find its units experimentally. Yeah.
Is the K units always going to be the same for third order?
Yep.
So
Yeah, so always first order has the unit of molarity or per second. 0 order is always molarity per second. Second order is always per molarity times seconds and so forth.
So if we can find the rate, or if we can find the exponent, we don't really have to do
You don't. I mean, you should be able to carry units throughout your math because you're AP chemistry. You should be able to carry your units out. But yes, you can always double check yourself because you memorize them. Okay. Okay. Let's do another one like this. Okay. You're gonna do your own table logic now. Okay. All right. There you go. First, make sure you write down some sort of form of work so that you can actually show how you can do this. Is in your packet. I know, but I want you guys to work on the process then. That's work through the problem. Stop copying the data table down. Work through the stuff. It's on your paper. That's why I print so you can do your classrooms and not make a data table copy.
Say the second one, and that's
I got A to the 0 power and B to the 3 power. So I don't get is that first thing is why are you like multiplying by 2? Because you're trying to keep one constant and then change the other. Okay, so you do the same thing on this side, obviously. Just to see what it's important. So when you do this one, why is it quadruple? I'm going to 0.6 times 0.4 times 4. So that answer quadruple. Here's the like individual base.
All right, a couple of you guys are moving on, right? So let's talk about the rate order, the rate law first, and you guys can do K. Right, back with me, because I'm going to show you the ugly algebra method too. I like to call it table logic and ugly algebra method. These are terms that I do not say table logic and ugly algebra method on the AP exam. Okay, this is just how I reference them. All right, so Jaden, tell me what you looked for first. Okay, so B was constant from trial 1 to 2. So then what occurred with A? A doubled. Okay, so for trial 1 and 2, what happened to rate? Okay, so it stayed constant. So what did you conclude here? I didn't mean to say times 0. I'm going to say times 1. It's 0 order. That's what I was going for. So basically, your mathematical processing is 2 to some power equals 1. Well, it's the only time you ever get 1 if it's to the 0 order. So A is 0 order. Okay. Emily, how'd you go next? Not quite sure yet. Who can volunteer for me? Qui? Trial 1 and 3. Okay. Between here and here, what happened? So we're looking for a constant, right? Because we want to independently kind of isolate one variable. So then what happened from B? It doubled. So what happened from rate 1 to rate 3? It quadrupled. So if you can't see 7 times 10 to the negative fifth and then 2.8 times 10 to the negative fourth is quadrupled, you can take the smaller number, meaning 2.8 times 10 to the negative fourth, divided by the larger number divided by the smaller number, which would be 7.0 times 10 to the negative fifth, and you would get 4. But that's essentially saying 7 is going to 28 if you move the decimal back. So that's going to be multiplied by 4. Okay, so 2 to some unknown power is equal to 4. So what's unknown power? 2. Okay, so then B is second order. So then write the rate law for me. K, A to the 0, B to the, how can I simplify that? K times concentration of B squared. Okay, so I just take A out of the equation. Yes, ma'am.
So on the first one, when you said base, why did you pick the A and instead of B?
So you have to look at both A and B at the same time. But you want A to stay constant while you're allowing B to change. And you want to see how B changing impacts the rate.
So you can't do this like when you're done.
If there's no constants. If there's no constants, you have to do the ugly algebra method. Okay, I'm going to show you ugly algebra with this scenario first, though. So you look for a constant with B. So if A is changing, A is causing rate to do nothing. So so rate is independent of A. A doesn't matter. A is 0 power or 0 order. B changes. Well, A stays constant, so we're disregarding A at this point anyway. But B changes by a ratio of 2, but rate changes by a ratio of 4, so that must be a larger order than 1. You with me so far? All right, so then you guys can plug into the rate law, solve for K. Let me show you the same method as ugly algebra. Okay, so this is where some people are going to, they're going to like this better than even the table logic. It takes a little bit more work, but it's a process that's a fail-safe. So when you do ugly algebra, I actually need some data points. Can you guys tell me the rate of, I can see this. All right, so I'm going to do rate 3 over rate 1. Okay? So what I'm doing is if I did not have the table logic in front of me and I couldn't figure it out on my own, I have to use another method. This is a secondary method. So you're always going to take the larger rate divided by the smaller rate, and that's why I'm doing rate 3 over rate 1. Okay? What is rate 3? 10 to the negative fourth molar per second, right? That divided by rate 1, which was 7.0 times 10 to the negative fifth molar per second. Well, rate we already know is equal to this kind of jumbled coefficient, or K constant and concentration. So I'm going to utilize that now. So here's the rate. It's equivalent to K or multiplied by a concentration of A to some unknown power, and B to some unknown power. So I put X and Y there, over K, A to some unknown power, times B to some unknown power. So what I have in front of me now is a system to solve for one variable that I don't know. So let's just pretend we don't know B. So we've already done the table logic and figured out A. What was A? You said A was what? Zero order, right? So I'm going to put zeros in there. Now, did we not say K was a constant? Yes? Okay, so K's on top, K's on bottom. What can I do? Cancel them because they're the same. A is to the 0 power, A is to the 0 power. Well, that just naturally is 1 over 1, so I can cancel them because they are the same. So now whittle down to just figuring out the concentration, or the exponent for y. It's really helping out here. Thanks. So everybody take this divided by this. What is this? 4, okay, is equivalent to, let's plug in values for B. Hey, Sydney, what's up?
We ended up running out of time, and we didn't get to interview Gigi.
You'll get to Gigi in a second. We got to finish our notes. AP Chem trumps everything. Bye. Okay, so it's the truth. Sorry. What is B for trial 3? What was the concentration of B for trial 3? It's on your data table. 0.2 to some Y power. What was the concentration for trial 1? 0.1 molar to some Y power. Okay, so if these numbers were more typical, we wouldn't be able to figure this out mathematically, or logically. So it's 0.2 over 0.1, 2, right? And so when you divide these exponents, then kind of coalesce together, so that's going to still be y to the, or 2 to the y power. So if I had to solve for y, not just looking at this and go, oh, duh, it's obviously 2, how would I be able to pull y, this exponent, out of the exponent area? Logs or natural logs, right? Either way, and when it would work. I'll do logs because you guys said logs. So I'm going to log both sides. Actually, let me just do this secondary row. This is called ugly algebra. So log of 4 times log of 2 to the y. Okay, so what does that allow me to do? Pull y in front of log. Okay, so log of 4 is equal to y log of 2. Okay, so isolate y. Divide by log of 2. Divide by log of 2. Okay, so then what's log of 4 over log of 2? 2. So 2 is equal to y, which tells us that it's second order. Sorry, I'm making whale sound. Yeah. For this one in particular, I started this off with that, but usually you can figure out one order really easily, and the other one could be more complicated if the rates don't work out so like just numerically as a full integer. So this would be your backup plan. Yeah.
Did you just look at so like 4 equals to the y and the right?
Yeah, but I did this for an easy example, but if I had like 3.8 is equal to 2 to the, or no, 3 to the x power, like I don't know what that is, right? So I'm showing it for an easy example, but you can use it for really complex examples. Yeah.
If you just put it into log form from there, and that's where you'll put it.
Say again?
If you just put it into log form straight from there, and that's where you'll put it.
Straight from where?
From like 4 equals 2 to the y. I put it straight.
No, I mean you could. I mean that's basically what we did, right? Am I not answering? It wouldn't change anything. It should work all the way through. Okay, let's do another one. Okay. This is phrased differently. Read first and write down as how it's phrasing the orders. You should be able to figure it out from the plans. I was just talking about the last K I didn't record. All right, Darcy, what you got for rate law? What are you doing? Taking a little lunch break? Anybody? Right, what's the rate law here? Go for it, Andrew.
6 times 0 times 10 to the negative 4.
I'm actually write the law with no numbers yet. So rate's equal to
Meter 4 over. Okay. Well, just the equation.
yes.
Okay, K.
Okay. So yeah, let me clarify that. When I ask for rate law, it's just rate's equal to K times the concentration variables. Yeah. Sorry, that's actually should be the easiest part for you guys, assuming that you read this question. Okay, so K times.
Concentration of A.
Actually, I have to use these now.
H.
The H2. Okay, so the hydrogen gas to the what power?
0.
2.
2.
Look, it's in the sentence. The rate law is. You got me? Rate law is.
First order. Okay.
Wonderful. Okay.
1 times NO to the second order. So that's 2.
Beautiful stuff there. Okay, so the sentence will tell you with what the orders are respect to. So utilize those. Use the individual reactants. Like they gave you no A's and B's here. They gave you the real deal here. And then that's what our rate law is. JT?
I was just gonna say, like, on the side, if you write, like, K, R2, H.
It doesn't matter which order it is, just put the K in the front like that. Okay. All right, so we have our rate equation, our rate law. Now, given this information, calculate the rate with the initial concentrations of NO and hydrogen gases blank and blank. Okay, so all I'm going to do is solve for rate, correct? So rate's this. So here we go. Rate is equal to, it tells you the rate law constant right here. So I'm going to utilize that as K. So I'm going to plug in 6.0 times 10 to the negative fourth per molar squared times seconds. You with me? Okay, just plugging in data. What's going to go here? I'm going to go in the same order here. So H2 is what? Yeah, so remember, it says respectively, like the NO is the first one, H2 is the second one, so this is H2. So 0.010 molar to the first, okay? And then 0.050 molar to the second, okay? You could do that in your head. You could use a calculator. Yeah.
Maybe 0.050 to the first, 0.010 to the second, because and that was just the first.
Yeah. And this is an O, right?
Yeah.
Isn't that what it's in, right?
Oh, yeah.
This is right. Okay. Sorry, I'm following through with the way I have it up on the board. Okay, so what'd you guys get? Numerically, what'd you get? Rate is what? 1.5 times 10 to the negative 8. What are the units? What did you say? Molar per second. Okay, so this molarity and this molarity, this molarity squared. So technically we have molarity cubed. A molarity cubed will cancel with molarity squared by canceling 2 molarities out, leaving us with 1 molarity on top and the second still remain on bottom. And that should make sense because rate is a molarity per second always. All right, so do not do math. Don't recalculate. Solve for the last one, not calculating the whole thing again, but using the law. And I got that, no run. Looking at the wrong problem. All right, Taz and Darcy, give me your logic here.
Okay, so we took the double thing, and then we basically put it into the equation, and we figured out that since it quadruples after you double it,
Okay.
then it's 4 times that, and then it turns into the rate, 4 times the rate.
4 times the rate.
Oh, no, it turns into negative.
Molar per second.
Volts.
Good, okay. So, good. So they just said, initially it says it's double to 0.1, so it was the 0.051. So if you took your concentration, so you had rates equal to K, H2, into, I'm sorry, nitrogen monoxide, but we're doubling it. So I'm basically just doubling this concentration, but this concentration is raised to the second power. What have we effectively done? So we've multiplied the whole rate by 4, so then we'll take this rate times it by 4, and we get 6.0 times 10 to the negative 8 meters per second. I'm just joking, it's milliliters per second. Okay, so you could do that, or you could replug in everything as we did up here, the K value, the H2 value, and the NO as given here, and you could recalculate the entire thing. Thumbs up, give me some questions here right now. Yes. Explain that one more time. So we saw this was we already saw for our rate law. Since it said that NO is doubled concentration-wise, I just said, okay, that's essentially just multiply my nitrogen monoxide by 2. Well, since this whole concentration, no matter what it is raised to the second power, if I multiply that concentration by 2, that effectively means I have 2 squared, which is 4. So if I multiply this side 4 times, that means the rate is 4 times bigger than what it was up here. So we solve for the rate here. I then just multiply this rate by 4 to give me 6.0 times 10 to the negative 8. You also could just replug everything in. It's just this one only changed one variable, so since we just did it, I just did one change here. Yeah. Hmm?
We just like ignore the into like because or the
Say again?
never mind. Just kidding.
Okay. I have one more I want to solve with you, but I'm going to bounce first to your problem set because we're getting to the time where I have to decide on which one. So we're going to go to your problem set. It's called differential rate law. It should be on the bottom half of this page. Okay. I want you guys to work through 1 through 6 right now. You'll probably get 1 through 3 done right now, and then I'll figure out what I definitely want you to do for homework. Okay. Work through 1 through 3. And then I'll do more examples here shortly.
But you do the rate and I'll give you a right rate.
Guys, focus. You have 10 minutes. Let's knock out 3 problems.
Basically 45 divided by 5. I do think that's also a problem when I that just adding. Sometimes you know like it shows physical demonstration. Oh, it took me long to make that my arm back. I could record it, but you know what? He takes the pass. So they what you got
People got everything about one thing.
yeah, really not such a great for all of them. I'm just pissed for me to give my brothers. I really got a nice 96, 97. He did. Near the end, they did great. That's like we were watching the stuff while we were.
Oh yeah.
So he was literally like flipping through my caps and was looking at the movie, just not getting paid. Did this like earlier. This is a very cool video. Hey, Andrew, don't say your grade.
Last year we were one.
Last year was worth one.
No, it was worth seven, but last year's where we made it work.
I feel like I would say your grade.
He didn't try it.
Focus on non
I got English to second. Yeah. Is that correct? I am so wrong.
Oh no, you're right. You're right.
I don't know. Also on my nine. I got it was multiplying by 9. So for the first, for the first concept, like you can solve around. It doubles here, okay? This also doubles, so that's one. And here, the second one, this is your constant. This is triples, but this value is 9, so you use 7 as your exponent 3 times.
Oh, yeah.
I mean, you're gonna get yours right there.
We have a wood.
Yes. Molar squared. That is another way to write it, yeah. Alright guys, here's what I want from you. Ready? But eyes up here, unless you can just listen and figure it out. Yes, you're doing 1 through 6 here, but you need to practice the repetition of looking at data 1 through 6. Answer keys on the bottom. I cut off the three harder questions. So you're doing 1 through 3 on the complex one, which is next. I'll help you with the 4, 5, and 6 next week, which are the harder ones. Of course, you can attempt them on your own time if you wish. So 1 through 6 on the first problem set, 1 through 3 on the one that's called initial concentrations, determine orders, reaction complex. And then you have 4 types of problems. So I think that's like 10 problems. So
You guys aren't gonna do it until Sunday at 10 o'clock. I'm not. Why? Bye.
We're doing another chemistry, you're like completely screaming of the band.
Hey, where you got? I am. I love the sauce. It's a great look. Really. Oh my god. Bye guys. Bye, ladies. Good questions today. Always insightful. Always insightful. Bye, Christian.
I'll see if I know what I'm doing.
What?
I said I'll see if I know what I'm doing this weekend.
Let me know. Just text me.
Okay.
I'm gonna go for it.
Okay.